Good afternoon, friends, and welcome again to another session of physics. Today we will be dealing with another very important chapter, that is dispersion of light. It is another part of optics. So today we will be discussing this particular chapter, dispersion of light. It is under optics, and optics already I have uploaded reflection and refraction and refraction. Already uploaded. So this is the third part of the optics, that is dispersion of light. So today we will be discussing with this. Before starting with this, it is my request, please keep following Parijat sir classes. And do like, share and subscribe the channel. Okay, so without wasting any time, let's move on to the chapter, because that is the most important thing. Let's move on to the chapter. Let's see what is dispersion of light. Okay, so first of all, see, here we are seeing that there is a prism. There is a prism, and here is a light which is entering the prism. This is the light which is entering the prism, and when it enters the prism, it makes an angle. It makes an angle I1, and then it suffers refraction and makes an angle R1, and then it comes out into the same medium and makes an angle I2. So this is the emergent angle, this is emergent angle, this is the incident angle, this is the refraction angle. Refraction at the first surface is R1, refraction at the second surface is, this is the angle of incidence in the second surface. So please watch that the path of the light, as you can see, it is entering the prism, then suffering refraction, and then again it is coming out into the air medium. This is air medium. Okay, this is air medium. So it is coming out into the air medium, and the direction of the ray is towards the base. The direction of the ray, emergent ray, is towards the base. So if I draw the incident ray along its original direction, and the emergent ray, if I produce back, I will see that the ray has suffered an angle of deviation this much, sigma. This was the actual direction of the ray. This was the actual direction of the ray, and the ray has come out like this. So what is the angle through which the ray has been deviated? This is the angle through which the ray has been deviated. That is called angle of deviation. Clear? And this is the angle of the prism. This is the angle of the prism. So angle A is the angle of the prism. So keeping this in mind, there are certain relations which you have to just remember. You don't have to derive any of these relations. You just have to remember that how are these particular variables related to each other. So first of all, R1 plus R2 should be equal to A. Where is R1? This is R1, the angle of refraction at the first surface. This is R2, the angle of emergence at the second, angle of incidence at the second surface. This is R2, this is R1, and this is A, angle of the prism. How are they related? This is how they are related. Second, how is the angle of deviation related? See, angle of deviation is related to I1 plus I2. I1, this is I2, this is I1 minus A. I1 plus I2 minus A. This is how the angle of deviation is related. Similarly, angle of deviation is also related to mu minus 1 into A. What is mu? It is actually the refractive index of glass with respect to air. This is the mu. It is the refractive index of glass with respect to air. Okay, so these are the three relations which I have written here, and you have to note these relations because lot of numericals are related to these variables. Next, let us move on to condition for minimum deviation. See, this is very, very important. Now, minimum deviation, condition for minimum deviation. I want that this angle should be minimum. I want this angle should be minimum. So what are the conditions for the minimum deviation? Okay, so let us write the minimum deviation relation sigma equal to I1 plus I2 minus A. Now, as you know that I1 can be written as root I1 square, I2 can be written as root I2 square minus A. Now this relation I can write, this is A square, this is actually A square plus B square, which I can write it as A plus B whole square minus 2AB. Using this, I have written is I can write it as A minus B whole square. I can write it as A minus B whole square plus 2AB. Okay, so this is what we have used here. This is what we have used here. So I'm showing it to you. You see, this is A minus B whole square plus 2AB. As you can see it, I have used this. Okay. Now, if I want that the angle of deviation should be minimum, this part should be 0. This part should be 0 because it is a square, and square always makes things maximum. So I have to remove this part. So if this is 0, I can write root I1 minus root I2 is 0. So root I1 equal to root I2. That means I1 is equal to I2. A very important relation. That means for minimum deviation, that means if you want that the deviation should be minimum, your angle of incidence and angle of emergence have to be same. The I1 and I2, as you can see, where is I1 and I2, they have to be same. Similarly, R1 and R2 should also be same. R1 and R2. If I1 and I2 are same, so automatically R1 and R2 will be same. So let it be R, and let I1 and I2 be equal to I. Okay. So using the first relation, which is R1 plus R2 equal to A, we can write R plus R equal to A. So R equal to A by 2. Similarly, in this relation, sigma equal to I1 plus I2 minus A, I can make it as sigma minimum because it is becoming angle of deviation is minimum when I1 and I2 are same, equal to I. So I plus I minus A, 2I minus A. Okay, so this is the condition, this is the relation when the angle of deviation should be minimum. The I1 and I2 should be same, R1 and R2 should be same angles. Okay, and angle of the minimum deviation should be 2I minus A. So from here I can write I is equal to this. Similarly, from here R is equal to this. So what is refractive index? It is sine I by sine R. Okay, as you know, all refractive index is sine of I by sine of R. So putting the values, I get another relation which is a very, very important relation. A plus sine A plus sigma m by 2 by sine A by 2. So please keep a note of this highlighted relations which are very, very important. Next, at minimum deviation. At minimum deviation, as I told you that I1 is equal to I and R1 is equal to R2. That is the incident ray, please watch here, the incident ray and the emergent ray make equal angles with the normal, because I1 is equal to I2. And another one is, what is the other condition? The other condition is the refracted ray is parallel to the base of the prism. The refracted ray is parallel to the base of the prism. So here you can see the refracted ray is parallel to the base of the prism. This is the base of the prism. The refracted ray is parallel to the base of the prism, and here is the minimum deviation angle. So this angle should be equal to this angle, and R1 should be equal to R2. Then only I can tell that it is the angle of minimum deviation, and the refracted ray is parallel to the base of the prism. This is the refracted ray which should be parallel to the base of the prism. Clear? Okay. Another important thing, please note here, that if I plot the angle of incidence and the angle of deviation, this is what? Angle of deviation. I will see that at a first, initially, as you increase the angle of incidence, see the angle of deviation goes on decreasing. The angle of deviation goes on decreasing. As you increase the angle of incidence, you see the angle of deviation goes on decreasing till at this particular angle of incidence the deviation becomes the minimum. The deviation becomes the minimum, and after that, if you increase the angle of incidence, then angle of deviation also increases. So please keep a note of this, that initially the angle of incidence, if you increase the angle of deviation, will decrease, and at a particular value it will become minimum, and then when you increase the angle of incidence, the angle of deviation will increase. So first it will decrease and then it will increase, and here it will become the minimum, and this is the angle of incidence at which it will become minimum, and this value is called the angle of minimum deviation. Clear? Okay. So next we want to study dispersion of light. Okay, so what is it? Dispersion of light. It is the phenomena of splitting of a beam of white light into its constituent colors on passing through a prism. This is the prism. This is the white light which is entering the prism, and when the white light enters, it splits into 7 colors. So what are the 7 colors? It is violet to red. So what are the 7 colors? It is Vibgyor. It is Vibgyor color, in which this is violet, this is indigo, this is blue, green, this is yellow, this is orange, and this is red. So these are the 7 colors in which white light will split when it passes through a prism, and that is called dispersion of light. Clear? Next we will see the cause of the dispersion. We will see the cause of the dispersion. We will see cause of dispersion. Now what is the cause of dispersion? What is cause of dispersion? Okay, refractive index is the main cause. Refractive index of the prism is different for different colors or wavelengths. Okay, so as you know here, this is the relation of the deviation mu minus 1 into a. For every different angle we know, see here, refractive index is inversely proportional to the wavelength. and we know that the wavelength of red light is the maximum and violet is the minimum. So for red, the refractive index will be the least, and for violet the refractive index will be the most. So definitely the deviation for red light will be the least and the deviation for violet light will be the most. So the cause is refractive index is inversely proportional to the wavelength. So since the wavelength of red light is the maximum, so its deviation will be the least, and the wavelength of violet is the minimum, so its deviation will be the maximum. So this is the cause of the deviation. So as you can see that the refractive index is inversely proportional to the wavelength. This is the plotting. As wavelength increases, the refractive index decreases. As wavelength increases, refractive index decreases. Clear? So let's see next one. Angular dispersion. What is that? What is angular dispersion? It is the deviation between the violet and the red color when white light passes through a prism. You see, this is the white light. This is the white light which is passing through the prism. Okay, and now we know deviation for the violet will be the maximum. This is the deviation for the violet, and for the red this is the deviation. So the difference in the deviations between the two, that is called the angular dispersion. Okay, that is called, we know deviation formula is this. So for violet light the deviation is this, for red light the deviation is this. Therefore for the angular dispersion, it is the difference in the deviation between the white light, between the violet light and the red light. Okay, so it is the difference in the deviation between the violet light and the red light. Next is angular dispersion. Depends on angle of the prism. See, angle of the prism, angular dispersion. This is the angular dispersion. This is the angular dispersion. Okay, so angular dispersion is violet light deviation minus red light deviation, and it depends upon what? The angle of the prism and the material of the prism. See, refractive index. Definitely it will depend upon the refractive index. Next is dispersive power. Another very important, dispersive power of the prism. Dispersive power of a prism, very very important. What is it? What is dispersive power of the prism? It is the ratio of the angular dispersion to the mean deviation produced by the prism. Okay, see the symbol omega, angular dispersion by the mean deviation. So this is the angular dispersion by the mean deviation. Okay, so this is how we write. So this is the formula for the, so this is the formula for the dispersive power of a prism. Dispersive power is the ratio between the angular dispersion and the mean deviation. Angular dispersion and the mean deviation. This is the dispersive power of the prism. Clear? And remember it please, omega has no units. Dispersive power has got no units. So this is the dispersive power without any units. Dispersive power depends on the nature of the prism. Definitely. See, only refractive index. Only refractive index is there. So dispersive power will only depend on the nature of the prism. Next, very very important topics these are. For deviation without dispersion. So please watch, what is it? Deviation without dispersion. What is it? That means in this case, suppose you have got two prisms. you have got two prisms like this. Okay, in one the refractive index is mu, and in the other the refractive index is mu dash. Dispersive power of this prism is omega, and dispersive power of this prism is omega dash. So they are telling deviation will be there. They are telling that deviation will be there, but dispersion will not be there. That means if this is the light, it will split up into the 7 colors. Again it will fall here. Again it will be there, and the light will come out like this. So see, there is no deviation. The light is actually going in its own direction. So if there is no deviation, sorry, I've drawn the wrong diagram. 1 minute. I've drawn the wrong diagram. So okay, we are doing deviation without dispersion. Okay, so dispersion will be not there. So let's first 1 minute. Okay, so let's, this is a ray, it suffers dispersion. This is the red and violet, falls here. We have done the correct one only, and then they will meet here. So you see, this was the actual direction of the ray. This was the actual direction of the ray, and now this ray has come like this. So this is the deviation. So this is the deviation. That means we have the deviation, but there is no dispersion, no splitting. Ultimately there is no splitting. So that is the condition for deviation without dispersion. Omega into sigma plus omega dash sigma dash is equal to 0. Correct? And net deviation, so without dispersion, so see, dispersion will not be there. So this is the net dispersion is 0. But what is the net deviation? The deviation of the first prism plus the deviation of the second prism. So this is the deviation of the first prism, and this is the deviation of the second prism. So please keep a note of this. This is our net deviation. Deviation of the first prism plus deviation of the second prism. And for the without dispersion, this is the dispersion condition. Net dispersion is 0. Okay, net dispersion is 0. So this is the deviation part, this is the dispersion part. Second, we will do dispersion without deviation. We are doing dispersion without deviation. That means now we will be doing deviation will not be there, but dispersion will be there. Deviation will not be there. That means if this is the prism, if this is the prism, that means if a ray of light is going like this, sorry, if a ray of light is going like this, this is the deviation. Again, so the ray will come out like this. For dispersion without deviation, that means dispersion will be there, but net deviation will not be there. That means the ray will I think, let me draw the diagram properly. This prism will be opposite, sorry, this prism will be drawn opposite. Okay, somewhat like this. That means here they are telling that you will have dispersion, but you will not have any deviation. You will have dispersion, but you will not have any deviation. So this is the net deviation is 0. That means I can tell that this is 0, net deviation is 0. So I will be telling that this is our 0, because there is no deviation. Please, we have to keep these in mind because these are very important. No deviations. And net dispersion. So this is the dispersion, net dispersion. This is the dispersion with the first prism. This is the dispersion of the first prism. And this is the dispersion due to the second prism. This is the dispersion due to the second prism. Means it is our omega, and this is our omega dash. Okay, omega and omega. So this is net dispersion is this, but net deviation, as you can see, this is our dispersion. Okay, as you can see, let me show you. This is our dispersion, angular dispersion. We have to keep this formula in mind. So what is it in terms of, so it will definitely be mu minus 1 into A. Okay, so if it is mu V minus mu R into A is this relation, so here, so that this is actually sigma B minus sigma R. So this is the angular dispersion, this is the angular dispersion, this is the angular dispersion. Clear? So angular dispersion can be written like this. So that is what we have written here. You see this. Clear? Okay. So now let's move on to another part, which is called the scattering of light. Okay, scattering of light. You just have to know this, that's it. Not very much questions come from here, but still it is the change in the direction of light. As you know that when this is the ray coming from air, and when it passes into the other medium, suppose glass, it will change its direction. So this was the direction, it is changing direction. So that is called the scattering of light. This is called the scattering of light. Intensity of light, intensity of the scattered light varies inversely as the fourth power of the wavelength. Please see. Due to scattering, the intensity depends on the wavelength in this way. Inversely to the fourth power of the wavelength. Fourth power of the wavelength. So I can tell, since the wavelength of violet is much less than wavelength of red, so I can tell intensity of scattering for violet is much greater than intensity of scattering for the red light. Clear? Next, rays do not undergo any change in the wavelength or frequency on scattering. Please note these 2 points. No change in the wavelength or frequency due to scattering. No change in the wavelength or frequency due to the scattering. Please keep this in mind. So what things do not change? One is a wavelength, one is a wavelength, and one is the frequency. Wavelength and frequency will not change anything due to scattering of light. Clear? Next is applications of scattering of light. So what are the applications of scattering of light? Number one, let's see, blue color of the sky. Why? Because see, wavelength of blue is less than wavelength of red, and we know if the wavelength is less, that means it scatters more. According to our this relation, it scatters more, so the sky will look blue. Second, white color of the sky means what? See, why is a sky, it is appearing white maximum times. Why? Because the clouds are very lower in height. They are seen due to scattering of light from the lower parts of the atmosphere, which contains dust particles, water droplets, etc. So all wavelengths, this is the important, okay, due to the presence of droplets of water, dust particles, so all wavelengths of light are scattered equally. So when all are scattered equally, we see it as a white color. All the white components of the light are scattered equally from the clouds, which contain dust particles and water droplets. Next is reddish color of the sky. Reddish color of the sky. Why does the sky look red during sunrise or sunset? At the time of sunrise or sunset, the sun is near the horizon. It is close to us, sun, near the horizon. The rays from the sun has to travel a larger part of the atmosphere. That means, see, during the sunrise or sunset, so here the sun is the farthest away from us. Sunrise or sunset, this is the horizon, okay, this is the horizon, the sun is near the horizon. So what happens, that color only can reach us which has the largest wavelength, and that is red. Only red color can reach us, so it looks reddish to us. Clear? Danger signals are red. Same thing. Danger signals are red because red is the maximum wavelength, so it will get least scattered. It will get least scattered. Intensity of scattering is very less, so it can travel large distances. That is why we use it as a danger signal. And next is conditions for rainbow. Please remember it, condition for rainbow, that is the observer must stand with his back towards the sun. This is the main condition for rainbow. The observer must stand with his back towards the sun. Clear? Now let us see certain numericals, so which we have already seen so many formulas. Let me show you. So please see, these are the formulas which we have done. R1 plus R2 equal to A, sigma we know, okay, minimum deviation angle we know, refractive index we know. Then we have seen this formula, that is the angular dispersion is mu v minus mu r into A. Then we have got the dispersive power, which is the angular deviation by the mean deviation. Okay, so which is this. So as you can see, all the relations, and this is important, please note here that if it is net deviation, this is the net deviation for us, net deviation without dispersion, and for dispersion without deviation we have shown it. So please keep a watch on this. So let us now move into the sums. First sum, it says that a thin prism of 6-degree angle, that means this is the angle of the prism given and this is the deviation given, refractive index. So this is the relation, sigma equal to mu minus 1a. Sigma is given 3 degree, a is given 6 degree. We can find the refractive index of the prism. Clear? Second, the angular minimum deviation for a prism of angle, this is a given and this is sigma given. Find the velocity of light through the prism. Okay, so first of all we have to find out the refractive index of the prism. So this is the formula. A is given pi by 3, sigma is pi by 6, pi by 3 by 2. So this is coming pi by 4 and pi by 6. Sine pi by 4 is 1 by root 2 and sine pi by 6 is 1 by 2. So from here we are getting the refractive index, and we know refractive index is also speed of light in air to the speed of light in the medium. So here light is coming from the air to the glass, so it will be speed of light in the air to the speed of light in glass. So speed of light in air we know 3 into 10 to the power 8 meter per second. From here we can find the speed of light in glass. Okay, let's move on to the next one. A prism of refractive index, so mu given, this is given to us, is placed in water of refractive index, that means this is given. Okay, as you can see I have shown it here, this is given, this is given. If the angle of the prism, that means this is the A given, find the angular minimum deviation in water, that means the prism has been put, in the water. So this is the prism which has been put in the water. That means, as you can see here, prism has been put in the water and the ray of light is coming from water to the prism like this. So they are asking you find the angle of minimum deviation. That means what is this angle? So first of all, since the ray is coming from water to the glass, we first have to know what is glass with respect to the water. So the formula is this, glass with respect to water formula is this. Please keep a note of this, a very important formula. Glass with respect to water is this. So putting the values, we get the calculations 1.15, and now using this formula we know this, we know the angle of the prism, we have to find the angle of minimum deviation, and calculating, as you can see that all the values in front of you, we have calculated it. This is 0.5, so it's coming 10.2 degrees. Please keep a note of it and see the calculations. I have done the calculations in order to save time and make the video as small as possible for you. Okay, so just I am discussing how you should be doing the numericals. That is very important. There is no use of wasting time in calculations. Okay, so this is how we calculate. This is 60 degree. This is 60. Okay, so this is how we calculate the angle of minimum deviation when the prism is put in water. Next, refractive index of flint glass for red and blue colors. Okay, for the red and for the blue, the refractive indexes are given. Find the dispersive power. So dispersive power is omega. As you know, omega is equal to mu b minus mu r by mu minus 1. Please note here the formula. Please note the formula here. It was actually mu v by mu r, but because here we are using blue and red, so we will write here mu b minus mu r by mu minus 1. So this is what is mu. Mu is equal to mu b plus mu r by 2, because it is the mean refractive index. Mu is the mean refractive index, and this is how we calculate it. Now putting all the values, we know that we find the dispersive power. Mu is the mean refractive index using the two colors. Next, dispersive power, that means omega is given to us, mu r is given to us, mu b is given to us. Find the refractive. So here we are finding, this is the formula. Okay, for yellow color. So we know that yellow is actually the mean color. Yellow. If we see VIBGYOR, if I see VIBGYOR, VIBGYOR, please watch here. Yellow will be considered as our mean color. Please note this. Yellow is considered to be our mean color. So that is why the dispersive formula changes. And now putting all the values, we found out what is the refractive index of for the yellow color. Next is a combination of two prisms. So there are two prisms, one of flint glass and the other of crown glass. Produces, very important, produces dispersion will be there. Dispersion is there, but deviation is not there. Deviation will not be there. Okay, so dispersion will be there, but deviation will not be there. So as you can see, they are telling that dispersions are there but deviations are not there. So here we know that this is the net deviation formula, which should be 0, and this is the formula for net deviation for flint glass and crown glass. We write it using the values which is already given. Refractive index for crown glass is given 1.52. for flint glass it is given 1.65. this is mu f, this is mu c given here, and using these values, angle for crown glass and flint glasses are given. Angle of prism for flint glass is, this is AF, and find the angle of crown glass prism. So AC we have to find. So this is how we find AC. And now they are telling, and the angular separation of red color and violet rays on emergence. So it is coming negative. What does negative means? What does negative mean? Negative means that the two prisms, that is they are put like this. Put like this. Okay. So this is AF and this is AC. They are put opposite to this. That is why the negative sign is coming here. Negative sign is coming. So now using angular separation, we know that this is the angular separation. So the net angular separation for this is for the crown glass and the flint glass. So we are using this formula. Now this is also this. Okay. So please watch how did this formula come. I'm showing it to you. Omega is equal to mu v minus mu r by mu minus 1. Okay. So mu v minus mu r should be what? Mu minus 1 into omega. So this is our mu v minus mu r. This is our mu v minus mu r, and that is into a, and then it was into a. Same thing here. So please note. Okay, so this is the dispersion. This is the angular separation into AF. So now putting all the values, we have found out, that is we know AC is given here. One thing will be angle of the prism, and we have to find out the dispersive power of for crown glass is given to us. Okay, so we have to do this 0.02. Here we have missed out 0.02. Okay, because it is the value of this, we have to multiply. This also we have to multiply. This is the angle of the prism. Angle of the prism is this. Okay, we already calculated, but we forgot to multiply this. So the value will be like this, and that is the net angular separation. Clear? Next is a crown glass of refractive angle, that means this is AC, is to be achromatized for red and blue light using a flint glass. What is achromatized? Achromatization means dispersion is 0. Net dispersion. So net dispersion will be 0. So what is that net dispersion? As we know that omega plus omega dash should be 0. That so omega for crown glass and omega for flint glass should be 0. Clear? So what is it? Omega is what? Mu v minus mu r by mu minus 1. Clear? Mu v minus mu r by mu minus 1. And also please note here, the net deviation is sigma v minus sigma r, which is mu minus 1 a this. That means it is mu v minus mu r into a. Clear? That means 1 minute. First I'm showing it to you here. Please watch it. Okay, so this is the thing. Please watch here. This is the net dispersion. This is the net dispersion Okay, please watch here. This is the net dispersion, and yes, so mu v minus mu r into A. So from here, the angle of dispersion, please watch here, the angle of dispersion, here is it. Okay, so that is why we are using this formula. This is our net formula for net dispersion. Okay, this is our net dispersion, mu v minus mu r into A, and mu dash v minus mu dash r into A. So keeping this, we are writing here, this is the formula. So this is net dispersion is 0. So using this formula, mu b, mu r, angle of the prism for crown glass, angle of prism for the flint glass, everything from here we found out angle of prism for the flint glass. Clear? Now net deviation is not 0. So this is our net deviation, mu minus 1 into AC. This is our net deviation. Okay, please go to the formulas which I have already shown you. Net deviation. Now putting all the formulas, AF is minus 3. We calculate this. Now please note here, what is this mu C and mu F? It is the mean refractive index. So how do we find that? Because we are using a blue color and a red color. So this is our mean refractive index for crown glass. This is our mean refractive index for the flint glass. And using these formulas. So when we are using these formulas here, value of this and value of this is being used here. Please remember here mu, when I am using this, this is the mean Ri of the two colors used. Clear? So next, see the next sum. A ray of light is striking is incident at an angle of 60 degree. This is incident angle given. Angle of incidence at one face of a prism of 30 degree prism, that means this is the A. The emergent ray makes, this is the angle, this is I1, this is angle I2. Show that the emergent ray is normal to the surface from where, that means I have to show that this angle is 90 degree. Because it is normal to, you have to show that it is normal to the surface. So let's see here. Sigma is given to you as I1 plus I2 minus A. Here we know the sigma, we know I1, we don't know I2. Okay, minus 30 degree. So I2 is coming 0. That means the angle of emergence is coming 0 degree. Okay, I'm sorry, this is not I2. They told that it is making 30 degree with the angle of incident ray. That means this is the sigma m. This is the deviation. This is the deviation. So I2 is coming 0 degree. That means it is perpendicular to the surface. If a ray is making no angle, that means the angle of emergence is 0 degree. So if it is 0 degree, that means it is normal to the surface. It is coming out at an angle of 0 degree with the normal. That means it is perpendicular to the surface. Now we have to find the refractive index. Refractive index is sin I1 by sin R1. Okay, so here they told that it is hitting at 30 degree at Yes. So please watch here that here R1, what is R1? This is 90 degree given, this is 90 degree given, clear? If this is 90 degree, see this is 30 degree given, this is 90 degree given, so this angle has to be 60 degree, but this angle is 90 degree, so the R2 is coming 30 degree. Okay, please watch here. This is 90, this is 30, so this should be 60, this should be 60, but we know this is 90 as it is perpendicular. So what is the remaining angle? The remaining angle is 30 degree. That means R2 is 30 degree. So R1 is 30 degree. So we know I1, we know R1. Putting the values, we get the refractive index of the material of the prism. Clear? Next, a 60 degree prism, as you can see that this is the angle A given, refractive index of the prism given. Calculate the angle of incidence for minimum deviation. Angle of incidence, that means they are telling calculate I1 for minimum deviation. Now, as you know, for minimum deviation, we know already that they are telling calculate the angle of incidence. Clear? So we know angle A, we know A. So what is the R for minimum deviation? As I told you, please watch here. The ray will go like this, it will be parallel to the base, and then it will come out. That means we have already discussed all these. This is our I1, this and this should be same, and this should be same, and we have already done that R is equal to A by 2. So that is how we find out the R, 60 by 2. Now refractive index is sin I1 by sin R1. So we don't know I1, we know refractive index. We can find out the I1, which is coming 49 degree. That means it is hitting at 49 degree, the angle of incidence. Second, angle of minimum deviation. So this is the refractive index formula. So we have to find this part. Refractive index we know, A we know. So putting all the values and calculating, we are getting the angle of minimum deviation is coming 30 degree, 38 degree. So please see the calculations here. Please go through the calculations. Similarly, the angle of emergence, that means I. Now we know at maximum deviation. So this is the condition, please. Not minimum deviation. It is not minimum deviation. So here, as we see, we can already find out for maximum deviation. Now please note this very, very important thing. For maximum deviation, I1 has to be 90 degree and R1 has to be the critical angle. Very, very important. And this relation already we have discussed in the previous refraction of light. Okay, let me give you a little bit hint. Please watch here. If any ray is striking at an angle, critical angle, then the refracted ray will be perpendicular. Or if any ray is striking at perpendicular along the surface with the normal, it will come out at the critical angle. Okay, and the relation of refractive index with critical angle is mu is equal to 1 by sin C. So taking that, so if a ray for maximum deviation, please watch, I1 should be 90 degree and R1 should be, if angle of incidence is 90 degree, as I showed you, this is I1, then R1 should be critical angle. And critical angle is 1 by sin inverse 1 by mu from here. So putting these values, refractive index we know, everything we know, we calculate that R1 is coming 42 degree. Now we know this relation A equal to R1 plus R2. I know A, I know R1, I can find out R2, which is coming 18 degree. Okay, so from this, now if I want to find the maximum deviation, angle of maximum deviation, so what is the maximum deviation formula? The maximum deviation formula is this. This is our maximum deviation formula. That is I1 plus I2 minus A. Okay, so we have to know A already we know, I1 already we know, which is 90 degree. We have to find I2, and that is why using this relation we can calculate I2. Using this relation we can calculate the I2, because the light is now going from the glass to the air. Light is now going from the glass to the air. Okay, from the glass to the air light is going, so it will be 1 by A mu G, which is 2 by 3. It was 3 by 2, it is 2 by 3. R2 I know, so from here I2 I can calculate it. Now using I2 and I1 we can calculate, this is the angle of maximum deviation. This is the angle of maximum deviation. Please watch the sum very slowly, pause it, understand it. You should know the other formulas also, then only you can do these numericals. So my request is, please pause my video, listen to the video, keep note of all the formulas in a page, keep the page in front of you, and then try to understand this. So next, let's see. A prism is made of glass of unknown refractive index. That means this I don't know. A parallel beam of light is incident on the face of a prism. By rotating the prism, the minimum angle of deviation is measured to be 40. So the angle of minimum deviation is how much? 40 degree. Angle of minimum deviation is 40 degree. What is the refractive index of the prism? Okay, so first of all, we know this formula. Okay, now please watch. A parallel beam of light is incident on a face of the prism. By rotating the prism, here they have given the refractive angle of the prism. Please watch here, A is given to us. So using this formula, we know A, we know sigma m, we know everything. We can calculate the refractive index of the prism. That means this we know. Now we know the refractive index, and they have given the refractive index. We know this value. We already know that they have put it in water, so we have to find now the ray will go from water to glass, so we have to calculate this, and that value is coming this. So using this formula now, when it is put in water, this is the thing which we don't know. They are telling if it is put in water, then what will be the angle of minimum deviation. So putting all the values here, we calculate the angle of minimum deviation to be 10 degree 8 minutes. Okay, we calculate the angle of minimum deviation to be 10 degree 8 minutes. So first of all, we calculated the angle of the refractive index of the prism. Now the prism is put in water. So what is the refractive index of glass with respect to water? Here we find out. Now this is the new refractive index of the prism because it is put in water. So now what is the angular minimum deviation? So here we know A, we know W mu G. So only sigma dash M we don't know. This is how we calculate it. So friends, with this we complete the refraction of light, that means dispersion. We have covered the dispersive power, we have covered the refraction through the prism, and we have covered the minimum deviation conditions. We have covered all the things regarding the prism, and we have done the angular dispersive power, the angular deviation, all these we have covered up. So I think you have understood it, and if you have understood it, please keep watching my channel. So that is a request to me. Please keep watching my channel, Parijat Sir classes, and like, share and subscribe it so that I can make more and more videos for you. And we have covered another portion of the optics, and please note the notes of the optics for the reflection and refraction already are uploaded, so please go through it and watch it. And my request will be, please keep watching it very slowly, keep a note of the things which I am discussing, and please try to write down the formulas and try to think the numericals on your own also. That will give you an immense help. Okay, so this is all from my side, and let's meet for again another session of maths or physics. As you all know that all the chapters individually I am uploading one by one. So till then, it's goodbye from my side, friends. Thank you.